Good afternoon. This is our narrated version of Chapter 10 PowerPoint, all about thunderstorms and tornadoes. So here we are looking at a map. This is from 2007, and this is average annual lightning flashes per square kilometer. So, gosh, does it tell us the time of year? Well, it doesn't. I guess this is just over the course of a year. So, do we see any kind of pattern here? Looks like we see a lot of lightning flashes in Central Africa, which is going to be within the tropics. Remember that the tropics extend from the Tropic of Cancer to the Tropic of Capricorn. So 23.5 degrees north latitude to 23.5 degrees south latitude. So it appears that we have more lightning strikes within the tropics and less so as we move north or south of the tropics. Also, it appears that we have much fewer lightning strikes over water than we do over land. And this is just a different way to look at this. This is lightning flashes on average per square kilometer per year, and the distribution looks pretty similar to what we saw on the last slide. So here we are looking at a map of the average number of thunderstorm days in a year. So who is winning here? It looks like Central Florida is getting more days with thunderstorms per year, average of 100. That's pretty significant. That's roughly a thunderstorm on average every 4 days, and it kind of makes sense. Remember when we were talking about lifting mechanisms and we talked about convergence? So you have in the daytime, particularly in the warmer months, you have a lot of heating over the land there in Florida. It's basically a big peninsula. So you have low pressure over the land and you have higher pressure on the water on either sides. So you're going to have air moving from the Atlantic towards the Florida Peninsula, and you're also going to have air moving from the Gulf of Mexico towards the Florida Peninsula. And this clash of air is a lifting mechanism. That air has nowhere to go but up. So we might expect to see more thunderstorm activity in Florida in general. And also we typically see more thunderstorm activity on the Gulf Coast than we do in other places. Ooh, look at the West Coast. Less thunderstorm activity indeed. Okay, so we discussed cyclones back in chapter 9, but also before that, I think maybe in chapter 6 or 7. Remember that a cyclone is just simply a low pressure center, and these things are going to rotate counterclockwise in the northern hemisphere. Low pressure is associated with warm, rising air that is less dense, and that's also going to bring you adiabatic cooling with height and reaching the dew point temperature, condensation, and cloud cover. All right, so a cyclone could be simply a low pressure center. It also could refer to the mid-latitude cyclones that we discussed in chapter 9 that are constantly forming, some often along the polar front, and then moving from west to east across the United States. Cyclone also refers to a hurricane, and what we think of as a hurricane, they are referred to as cyclones in the Indian Ocean and typhoons in the Western Pacific. Okay, how about the Eastern Pacific? Well, those will be hurricanes just like they are in the Atlantic. And of course, a tornado is technically a cyclone. I mean, it's a very intense, rapidly rotating center of low pressure. So there are basically two types of thunderstorms. Yes, this is an exam question. You have what we refer to as air mass thunderstorms, which are your typical everyday thunderstorms. So you just need warm, humid air that is rising. Okay, so any kind of lifting mechanism could be in place, or it could just simply be, localized convective lifting, that you just have these hot pockets of air that are rising We could say they are in an unstable environment, and of course, we expect to get cumulonimbus clouds. These are associated with maritime tropical air masses, and we tend to get a lot of air masses east of the Rocky Mountains, especially in the warmer months. So this has a little something to do with that map we looked at earlier, where on the west coast of the US, they have much fewer thunderstorms or lightning strikes than we tend to have east of the Rocky Mountains. And why is that? Well, they're generally not getting affected too often by maritime tropical air masses. Okay, so those are our air mass thunderstorms. By the way, air mass thunderstorms, we tend to get more of them in mountainous areas because, of course, if you have a mountain in place, then you have orographic lifting in place, and that can lead to thunderstorm activity. Our second type of thunderstorms are referred to as supercell thunderstorms. Okay, I know you on that purple bullet there it says severe thunderstorms, but technically we're going to refer to these as supercell thunderstorms. So these are not your typical everyday thunderstorms. They're going to have, high intensity rainfall, which can lead to flash flooding. The possibility of hail is there, high winds, and the possibility for tornadoes. So we tend to get our supercell thunderstorms forming along cold fronts. No, not every cold front that comes through is going to give us a supercell thunderstorm, but some of them do, particularly in the warmer months. And basically what you need to produce a supercell thunderstorm is you need a big difference in the two air masses. You need a big difference in the temperature and moisture content of that maritime tropical air mass clashing with the continental polar air mass along a cold front. So supercell thunderstorms are one of our locations in which we might expect to get tornadoes. And this is basically a repeat of what we looked at on the previous slide. So again, exam question here, what are the two types of thunderstorms? Air mass thunderstorms and supercell thunderstorms. So here you're looking at the development of a thunderstorm. So that one image there to the left, labeled A, cumulus stage, that's not just cumulus, that would be cumulus congestus. Remember back when we talked about clouds? And our cumulus, we really had two types. Cumulus humulus is your typical everyday cumulus cloud, those puffy white clouds that look like cotton balls in the sky. But cumulus humulus means that you have some lifting going on and you're starting to build a taller cloud. So is it possible with enough instability in the atmosphere that a cumulus humulus cloud could build into a cumulonimbus cloud and a thunderstorm? The answer is yes, absolutely, that can happen. Stages in development. We will touch on this, but you're not going to have this on your exam. You're not going to need to know the stages in development, but let's go through these anyway, just for our learning, just to learn something. Okay, so number one, it's called the cumulus stage. So a cumulonimbus tower develops as water vapor moves from the surface to greater heights, lifting mechanisms. And of course, as that air mass continues to rise, it's going to cool, you're going to hit the dew point temperature, you're going to have more condensation. And remember that condensation is releasing latent heat energy, which warms that air mass even more, so it can lift to higher and higher heights. So your developing cloud tower needs a continuous supply of moist air to develop into a cumulonimbus cloud. So in the cumulus stage, where you're building a thunderstorm, updrafts are going to dominate. Now you're going to get downdrafts at some point as well, and downdrafts are forming via entrainment. And entrainment just means that you're mixing in cooler, dry air that you might have, say, at the surface, as a turbulent flow captures cooler air that is not quite so turbulent. That can form downdrafts. Downdrafts can be very problematic to aircraft, particularly if they are taking off or landing. So here we are looking at, on the top left, those are just your cumulus homulus clouds, fair weather clouds. And of course on the right, you're looking at cumulus humulus, you're looking at cumulus congestus on the right, that is developing into a cumulonimbus cloud and looks like we are building a thunderstorm. So the mature stage of your thunderstorm is the most intense. This is when you're going to get very heavy rainfall, high intensity rainfall events. You might get hail. You may not get hail. It's possible that you will. And you're going to have cool down drafts existing next to updrafts. Now the dissipating stage is where your thunderstorm starts to break apart. And this stage is dominated by downdrafts and entrainment, causing evaporation. Remember that evaporation is absorbing latent heat, so you're taking heat out of that air mass, so it's not going to continue lifting. So it will not continue to keep up the thunderstorm mature stage. It'll start to dissipate. So our supercell thunderstorms, yes, sometimes the weather reporting stations might refer to them as severe. Supercell thunderstorms, the kind of thunderstorms you might get along cold fronts. What are you expecting to get? Heavy downpours. Flash flooding is always possible. You could get very high-speed wind gusts, straight-line wind gusts. Lightning you're absolutely going to have, and thunder. Hail is possible. Wind shear. Now the problem with wind shear is that wind shear can lead to the formation of tornadoes. And of course, with our large thunderstorms, remember that cumulonimbus cloud can overshoot into the stratosphere a little bit. And as that thunderstorm is moving into your area, what you're first going to experience are going to be downdrafts. That is part of the gust front. And you will feel these here at the surface as fast winds. So here's a nice cross-section drawing of one of our more violent thunderstorms. And this is really a good drawing because it's showing you that you have this cold air quickly coming down from the thunderstorm. That's a downdraft. And it's going to kind of scoot out in front. And basically, that gust front is going to act as a lifting mechanism. So as this thunderstorm is, generally traveling east in the westerlies, as it's moving into your area, it's going to undercut any warm, moist air that's in front. So the gust front from the thunderstorm is also a lifting mechanism, and this can help keep the thunderstorm going because, again, any lifting mechanism you have here with this warm, moist air, as it's rising, it's cooling adiabatically. Condensation is occurring, you're releasing latent heat energy, adding buoyancy to that air mass so that it can grow ever taller. Now this is a roll cloud. This picture here on the left, I don't think I've ever seen a roll cloud or a shelf cloud in person. I've seen plenty of images of them on the Weather Channel or, in textbooks. I've never seen one in person, but a roll cloud sometimes will form with your thunderstorm as it's moving in, and it forms in the eddy between the inflow and the downdraft. So it's kind of there, maybe just above the gust front, and you can form these eddies or these circular currents as you have that warm maritime tropical air mass being forced upwards. I don't know how common it is to get roll clouds around here. I want to say out west in the Great Plains, those are more common. So something that I mentioned earlier, in the mountains, you tend to get more air mass thunderstorms than in flatter areas. And I know this to be true from growing up in the Appalachian Mountains. And they definitely experience a greater number of air mass thunderstorms. And it's just simply because the mountain itself is going to act as a lifting mechanism, orographic lifting. So your supercell thunderstorms, again, these are only going to form along cold fronts, and not every cold front is going to form a supercell thunderstorm. They're more likely to happen in the warmer months when you have a greater difference in temperature, air pressure, and moisture content between the maritime tropical air masses and the continental polar air masses that are meeting at the cold front. So your supercells are the most violent thunderstorms, and they consist of a single powerful cell that can extend to heights of 20 kilometers or more. And these supercell thunderstorms can be quite large as well. They can measure 20 to 50 kilometers in diameter. So we're looking here at a nice cross-section drawing of a supercell thunderstorm. So your gust front is labeled here as your downdraft. What they're not showing so much is the lifting that's going on. Again, this gust front is basically going to move forward and scoop that warm, moist maritime tropical air up as it goes. You see the storm direction there, and don't forget that the anvil, that pointy part of the cloud, is always pointed in the direction that the storm is headed. So what we have in here is a mesocyclone. Notice that kind of in the middle of the cloud there. A mesocyclone is a rotating updraft. And if you have these rotating updrafts in your supercell thunderstorm, then it's more likely that a tornado is going to form. So in the top right, that is, I'm assuming that's a satellite image of supercell thunderstorm in action, and of course, bottom right, that is a tornado. Okay, so again, the supercell thunderstorms, you can skip that first part there. That is a repeat. So the mesocyclone. Again, a mesocyclone is basically a rotating updraft, and this has to do with vertical winds. So you have updrafts and downdrafts within your thunderstorms, and particularly within your supercell thunderstorms. And this can cause the updrafts to rotate. So tornadoes will often form within the mesocyclone and then touch down at the surface. There are other means by which tornadoes can form, and we will get to that on a later slide. Okay, so squall lines are narrow bands of thunderstorms that can be produced in the warm sector of a mid-latitude cyclone. And this is going to involve the dry line and the continental tropical air mass. We discussed this in class this past week. So remember, the continental tropical air mass is hot and dry, only around in the warm months, forming in Mexico, Central America, and then migrating into the desert southwest of the United States. So continental tropical air is pulled into the warm sector of a mid-latitude cyclone. So remember, we looked at an image in the PowerPoint for Chapter 9 where the dry line is going to form in between the warm front and the cold front of a mid-latitude cyclone. And remember that dry air is more dense than moist air. So the continental tropical air mass is more dense than the maritime tropical air, and therefore it will undercut the maritime tropical air, and that's another lifting mechanism. And of course, lifting mechanisms can lead to thunderstorm activity. So sometimes you might notice a squall line coming if you see something they refer to as mammatus skies, or mammatus skies. I think that's how the Weather Channel pronounces it. And this is not something we typically see in North Carolina. I have never seen mammatus skies in person. I've seen pictures of them or video on the Weather Channel. This is something that's happening in the Midwest, where you are likely to experience the continental tropical air mass and the dry line. Squall lines, typically forming along the dry line. So this map is kind of similar to one that we looked at in the last chapter, Chapter 9. We were talking about our mid-latitude cyclones and the dry line. So again, this is happening in the summer. This is not affecting all parts of the United States. There's a reason why here in North Carolina, we don't ever hear about the continental tropical air mass of the dry line. We just don't experience this as far east as we live. But along that dry line there, where the continental tropical air mass is gonna undercut and lift the maritime tropical air mass, that's where you can get these squall line thunderstorms, and these squall line thunderstorms are capable of producing tornadoes. Here's another image of the squall line forming. Notice the states that are involved here: Texas, Oklahoma, New Mexico, Arkansas. So again, this is something that we're not so used to here on the East Coast. So what do mammatus clouds look like? This is what they look like, and they're called mammatus clouds because, well, yeah, basically they're forming, or they're referring to cows that are, nursing their young, or that are being made to be in that state perpetually because they're on a milk farm. Anyway, they basically look like cows' udders. So again, I have never personally seen a sky looking like this because I have not, I have traveled west occasionally, and I guess I just didn't experience a thunderstorm when that happened. Maybe some of you, have lived out west or have visited family out west and have seen such a thing. But if you ever see clouds like this, that means that squall line thunderstorms are likely going to move into your area. So this is a satellite image of a mesoscale convective complex, which is basically referring to, it's another way to think of squall line thunderstorms, where you have this long line of big thunderstorms, and they're long-lived, and then they are moving east across the United States. So mesoscale convective complexes, also referred to as MCCs. This is another type of supercell thunderstorms. In this case, you have basically several supercell thunderstorms that are kind of all organized into like a large oval or circular cluster. This is a very large organized set of storms covering an area of 39,000 square miles. And again, these things tend to be long-lived. So they can move slowly, and they can last for 12 hours or more. And that's just devastating to think about, because that's a whole lot of area that these storms can cover. And when they are moving across your area, they tend to move a little bit slower than your typical cold front thunderstorms. And that means the likelihood for flash flooding is greater. And these things tend to form mainly in the Great Plains. Think about our traditional tornado alley. Okay, so microbursts. Microbursts are basically a type of downdraft, and that scary image there in the top right shows what can happen to airplanes when they are trying to land in a thunderstorm and they get caught in one of these microbursts. And then that photo to the bottom right, you can visually see the microburst there as it's accompanied by incredibly heavy rain. So flooding in general, flash flooding, is basically one of the worst natural hazards that we have on this planet, and it kills an incredibly large number of people every year. Yeah, flash flooding. I mean, we generally think of tornadoes or hurricanes or maybe earthquakes and tsunamis as being the worst types of natural hazards, but flash flooding can happen in so many places. And it doesn't have to be part of a hurricane. There don't have to be tornadoes involved, and these events can be widespread, and they can be quite deadly indeed. So this is an interesting pair of graphs here. So the one on the top left is showing what happens before urbanization. So an area that has not yet been converted into another city and you haven't paved everything versus the graph there on the bottom left, which is after urbanization. So what we're showing here is basically that the lag time between your beginning of your thunderstorm activity and flash flooding, the lag time is longer before urbanization, and the amount of discharge or overland flow that you get is less. So basically what we're saying here is that urbanization increases the likelihood of flash floods because you pave a lot of surfaces and they are now impervious, and the ground cannot absorb as much rainfall. And then of course look at the image on the right. That's incredible. You have there the Las Vegas Fire and Rescue, and there's flash flooding in this area, and these firefighters have headed out to help rescue people trapped in the flood, and now the firefighters themselves are having to be rescued from the flood. Okay, lightning. So I recommend maybe pausing on this slide and reading through this. We might just go through this a little bit, but this is lightning casualties in the United States by location or activity. Okay, so open areas. Open areas are dangerous places to be when there's a lightning storm. Trees, we might want to seek shelter under trees to keep dry from the rain, but that's a potentially dangerous place as well because, you might, especially if you're leaning against the tree, touching it, but even if you're not touching it, you're just in close proximity, the trees will tend to get struck by lightning. That's not a safe place to be. Of course, on the water is not a safe place to be during a lightning storm. Golfing is not safe. Outside in farm or construction vehicles, especially if you have an open, exposed cockpit. Corded telephones. I know there's not a lot of corded telephones around anymore, but some people do still have them. And it's incredibly dangerous to talk on a corded telephone during a lightning storm. It's also dangerous to be in the shower or at the sink washing your hands during a lightning storm. All right, so supposedly you have a greater chance of getting struck by lightning than you do of winning the lottery. That's an incredibly scary thought. Okay, so there's going to be a handful of slides here that are dealing with the setup for lightning strikes from cloud to ground. This is not going to be on your exam. We're just very quickly going to go through this since this is not going to be on your exam. But basically, lightning strikes have to do with the separation of charges. Okay, so top left there in your cumulonimbus cloud, the charges tend to separate and you get a lot more negative charges towards the bottom of the cloud, positive charges towards the top of the cloud. And then at the ground, and this is all due to ionization, at the ground you tend to have a lot of positive charges. So notice that you have opposite charges here between the base of the cumulonimbus cloud and the ground, and that's a dangerous situation. So the first thing that happens is that step leaders form, and they're ionizing the air, and they're basically forming a path of conductivity. Okay, so the bright return stroke, which is what we see, begins to carry the charge which has been deposited on the path downward. Something that I first learned in a Physics 2 class many years ago at West Virginia University. What you see, which is the return stroke, it always looks to us, I mean, it's very fast, Maybe it looks to us like it's coming from the cloud to the ground, or maybe we just assume that. But the flow is actually from the ground going up to the cloud. And then, of course, you've had one lightning stroke, and that takes care of some of the separation and charges, but as long as your cumulonimbus cloud is still there and this thunderstorm is still kicking, it's just gonna reionize and you're gonna make another path to set up for the next lightning strikes. All right. Nothing really on this slide that's gonna be on our exam. How long does a flash last? A few tenths of a second. We can definitely see it. And while it might look to us like one lightning stroke, it actually can be multiple. And the step leader is invisible to us. We don't see that, but that's extending from the cloud down to the ground. And then again, what we see is the return stroke from the ground to the cloud. Now, believe it or not, 80% of all lightning strikes are from cloud to cloud. Okay? Actually, I take it back. That last bullet, you might write that down. That is going to be an exam question. Sheet lightning. What is sheet lightning? Not to be confused with heat lightning. We'll talk about that later. But sheet lightning is lightning from cloud to cloud. And most lightning strikes are actually from cloud to cloud. But we do also have them from cloud to ground as well. And again, they can be quite deadly. Which kind of begs the question of flying in an airplane through a thunderstorm. Is that ever really the safest option? Perhaps not. And sometimes the pilots just don't have any other choice, and that's the only path they can take is to fly through a thunderstorm. But the planes do stand the risk of getting struck by lightning when they're flying through a thunderstorm, and you have a lot of this cloud to cloud lightning going on. So of course, thunder is the sound that we hear, and don't forget what happens first. Well, you see the lightning first, and then you hear the thunder. And of course, light travels a lot faster than sound. So that sound that you hear, and everybody knows what the boom of thunder sounds like, and it's because the air surrounding that lightning stroke is heated quickly and to a very high temperature, as hot as 33,000 degrees Celsius. So that air is going to expand explosively, and that is what produces the sound waves that we hear as thunder. Now, if the lightning is more than 20 kilometers away, you will not hear the thunder. Okay, and that is what we know of as heat lightning. Lightning that you can see but you can't hear. Why do they call it heat lightning? I have no idea. I don't think it has anything to do with heat. It just simply means that sound is going to dissipate pretty quickly. So you can easily see lightning that is far enough away that you're not going to hear the thunder. All right, and this is a similar image, similar to a couple that we looked at earlier in this presentation. Definitely more lightning strikes over land than water, just telling us that that separation of charge is going to be easier to achieve over land than over water. And you might think, well, maybe we just don't have thunderstorms forming over water. Well, that's not the case. We absolutely have thunderstorms forming over water all the time within the tropics. Which kind of begs a question, so let's back up here and go to that previous slide. Are they giving us some cutoff here as to how many? That kind of begs a question. How many miles away must that lightning be for you not to hear it? I'm just not sure. So here's something that's not on your exam, but a good question. Is there anything beneficial to lightning? Well, yeah. I mean, there's a lot of ways in which lightning is destructive, including that lightning will occasionally start some of the forest fires that we see in the western states. Sometimes those are human induced because of down power lines or gender reveal parties that have gone awry. But lightning does cause some of the out of control forest fires that we see in the western states. So does lightning do anything good? Well, it's part of nature's nitrogen cycle. So lightning discharge creates tons of fixed nitrogen compounds from atmospheric nitrogen in the air. And, you know, these are valuable fertilizing agents. Okay, so we're moving into tornadoes now. That's exciting and scary at the same time. So everybody knows what tornadoes are. Basically, they're very intense low pressure centers. So violent windstorms with a rapidly rotating column of air, which you might refer to as a vortex. So there's a big pressure difference here. So the pressure within the tornado can be as much as 10% lower than immediately surrounding the storm, and that is actually quite significant. Sometimes it's just one vortex. Sometimes it's consisting of multiple vortices. And something that is necessary for tornado formation is wind shear. Now, sometimes you'll hear the Weather Channel folks talk about, the likelihood of an invest in the Atlantic or Caribbean becoming the next tropical storm or hurricane, and they might discuss wind shear. If wind shear is present, say in the Caribbean or Atlantic, that's going to inhibit hurricane formation. But if wind shear is present in your supercell thunderstorms or your squall lines, well, wind shear is necessary to form tornadoes. Okay, so actually let's skip this class. Let's skip this slide because this is in our metric units. We'll see something similar to this coming up later in the American units that we are used to. Okay, so here we're looking at the center of a tornado that has multiple suction vortices. Tornado development. All right, so when we talk about this in class, and hopefully we'll have time to talk about this this coming week, the one time that we meet, I will try to demonstrate with a pencil or pen one means by which tornadoes can develop. So wind shear, what does that really mean? Okay, it means a couple of things. So this drawing here is only showing one type of wind shear. So in the top left, they're labeled A. That is a type of wind shear where you just simply have a difference in the wind speed. Okay, so at the surface, you have weaker winds. They're not moving as quickly. And then higher above that, higher up in the troposphere, the winds are faster. And this makes sense. We've discussed that friction at the surface is going to slow down wind speeds. So wind speeds are always faster as you move up away from the surface. So this is one type of wind shear, where it's just simply wind moving the same direction but at different speeds. Another type of wind shear can happen when you have winds that are blowing, winds at the surface blowing perpendicular to each other. And I will demonstrate this in class for us this week. Anyway, so you end up with wind shear. What the wind shear does is it creates this horizontal spinning vortex, okay? And that might sound kind of scary, but it's actually really not that bad. If that horizontally spinning vortex at the surface gets pulled up vertical by an updraft, then you have a tornado, and then it is a problem. So again, wind shear is necessary for tornadoes to form. And we do expect wind shear when we have a mesocyclone present within our thunderstorm, particularly our supercell thunderstorm. So here are some really old images. We'll have some more recent images to look at. I guess this isn't that old. No, this is 2011. Yeah, it's not that old. All right, so Joplin, Missouri was hit by a F5 on the Fujita scale tornado back in May of 2011. And I mean, the devastation was just total and complete. Even brick homes, which can withstand stronger winds, even the brick homes were just torn to pieces. So this is a case study, basically. This goes all the way back to 2003, Manchester, South Dakota. So this is a pressure change of 100 millibars, which is extreme, in just 40 seconds over a particular location where they had an instrument reading. And it was an F4 tornado passing over this particular probe, showing just what a difference in air pressure you have between the center of that tornado and, on the outside. And it's this huge pressure difference that makes those winds so strong. We have seen this before. Okay, so factors in formation. I'm going to want you to know something about this for your last exam. I'm going to ask you to know which particular storms are capable of producing tornadoes. So let's go through the list, not all of which are written down here. Definitely you need the presence of wind shear, of course. You need a thunderstorm, particularly a supercell thunderstorm. So tornadoes are likely to form either in a supercell thunderstorm or along a dry line where you have that continental tropical air mass undercutting the maritime tropical air mass. And of course, squall lines involve the dry line, so you can get tornadoes along your squall lines as well. And something not listed here is that tropical storms and hurricanes can also produce tornadoes. Okay, because tropical storms and hurricanes, while the presence of wind shear might inhibit those things from forming, you still have wind shear associated with your tropical storms and hurricanes. So tropical storms and hurricanes can also form tornadoes, and we see this quite often when tornadoes hit North Carolina. Sorry, when tropical storms and hurricanes hit North Carolina. Sometimes they bring tornadoes. The one good thing about the tornadoes that form in tropical storms and hurricanes is that they tend to be less powerful, smaller, and shorter lived than the tornadoes you get along your supercell thunderstorms or squall lines. All right. Yes, so your squall lines are dry lines, cold fronts, but also tropical storms and hurricanes are places where tornadoes can occur. Okay, here we go. No, this is still in the metric units. So we'll skip this. We'll see this in English units at some point. This is okay, the image on the left isn't that great, although it's just trying to show wind shear. So the image on the right is pretty decent at showing how wind shear, in other words, here you have just slower winds at the surface getting faster as you move on up in the troposphere. Wind shear can basically create this horizontal rolling tube of air. And again, as long as it's horizontal, it's not that big a deal and it's not that destructive. But if this horizontal rolling tube of air gets pulled vertical in an updraft in your supercell thunderstorm, then you have a tornado. Okay, so this is actually a really old map. I mean, this comes from the version of the textbook that we were using when I first started teaching this class, which is probably 11 years ago. So yeah, this probably needs to be updated. But this is a map of average annual tornadoes per 26,000 square kilometers. Okay, so can you find Tornado Alley on this map? Of course you can. It's there where you got the 9.0 and the 8.0 and the 7.0. So the red is 9.0, the orange is 8.0, the brown is 7.0, and so on down. So clearly you can see Tornado Alley there. And Florida is a place where you can have tornadoes, and even in North Carolina. What you sort of see in this map, but would be more evident in an updated map, is what they refer to as Dixie Alley, which is saying that even east of Tornado Alley, in your southern states, you can get tornadoes. And again, I think this map is a little bit outdated. And then now look at the graph in the top left there, and there they're kind of showing you throughout the year. So April through June, as in April, May, and June, these are the months that you are most likely to have tornadoes. I recommend pausing this presentation and reading through this. So this again is kind of outdated. Does it even include 2011? It does. Okay, because you've got April 2011 on there. Anyway, so this is just kind of showing you some extreme aspects of tornadoes, like the deadliest tornado outbreak, which was back in 1925. The biggest 24-hour total tornado outbreak back in 74. The calendar month with the greatest number of tornadoes, April 2011. 2011, by the way, was probably the worst year for tornadoes in all the years that we've been keeping records of tornadoes here in the United States. Highest recorded tornado wind speed, 302 miles an hour. Yeah, that's like a high up in a F5 tornado, and that was in 1999 in Oklahoma. Highest elevation tornado. A tornado in Sequoia National Park, California. California is just not a place you really associate with tornadoes, but occasionally they get them. Okay, so what you see there in that first short paragraph is exam material. Tornado season. We're putting season in quotes. It's not really an official season like hurricane season, but the time of year that we are most likely to get tornadoes is April through June. That is an exam question for sure. So why in the spring? Because that's when you have your greatest temperature, pressure, and moisture contrast between your maritime tropical air masses and your continental polar air masses. So spring is a dangerous time in Tornado Alley and Dixie Alley. Are we part of Dixie Alley? Yes, actually we are. Okay, so we will quickly go through some slides here looking at tornado destruction. That image on the right is just crazy. We know that that was a vehicle. We see the tires and the chassis. Most of the rest of that vehicle has been ripped off. Look at that image on the left. You got a piece of metal that has been basically impaled into a telephone pole. And that only happens in the presence of very high wind speeds. Okay, you can't just walk up to that telephone pole with a piece of metal and just get it to magically stick in there. It requires intense wind speeds for that to happen. So this image up here in the left is actually a really good map. 4 key ingredients for Tornado Alley. So what do you have? Well, you have continental polar air coming down from Canada. You have maritime tropical air coming up from the Gulf. In the warm months, you have continental tropical air coming up from Mexico. And remember that from north to south, here in the middle of the United States, there are no barriers. So this air can freely travel north or south. So you get clashes of these air masses. And then, of course, what you get out of this is you get, well, your mid-latitude cyclone with your warm front and your cold front. And then in the warm months, in between the warm and cold front, you get that dry line, which is another lifting mechanism. And this just really sets everything up for Tornado Alley. Okay, now these images here, I believe, are older. These are older than 2011, probably going back into the 90s, I would believe. And this is a tornado outbreak damage that happened in, this is in Illinois. Okay, so there's a question here. In which corner of the basement should you hide? Okay, if you are in a building and a tornado warning is issued, if that building has a basement, that's the best place to hide. If there's no basement, then they say you want to be in a first floor On the first floor, you want to be in an interior room with no windows. They say bathrooms are good, you know, if it's a bathroom without windows, and to maybe get in the bathtub and drag a mattress and put that mattress over you to protect you from things that might, you know, fall on you if the roof collapses in. But let's, you know, or if you have an outdoor underground storm cellar, and is there a particular corner that you want to hide? And from looking at these arrows and the average tornado track across, I think that's Illinois, I think that's what state they're representing there, you would probably want to be in the northeast corner of the basement. Okay, we have seen this slide before, so we will skip it. This goes back to, I believe this is 1925, the tri-state tornado outbreak. This was incredibly deadly. This was one outbreak that killed in total over 700 people. And this went from Missouri into Illinois. Yeah, this was a big deal. We've seen this before. Okay, so the Fujita scale. No, you don't have to memorize this or anything, but just have some idea. It goes from EF0 all the way to EF5. And as you, I do recommend maybe pausing here and taking a look at this this table. So it gives you an idea of how fast the wind speeds are in miles per hour. So yes, there is such thing as an EF0. If you're going to have a tornado, that's the one you want to have. But just look at those wind speeds, 65 to 85 miles per hour. That's absolutely, well, that's almost 2 and just over the threshold for Category 1 status in a hurricane. And then on the far right, it tells you what kind of damage you're going to have. Even just an EF2, the damage can be considerable. Single-wide mobile homes destroyed. Permanent homes might shift off foundations. Softwood trees can be debarked. Even an EF1 can overturn single-wide mobile homes. Here's the thing. A mobile home or a vehicle of any kind is not a safe place to be in a tornado. That's just an unfortunate fact. All right. Moving on. This is an interesting little graphic here, but it makes perfect sense. So, you know, most tornadoes in a given year are going to be the weak ones, an EF0 to an EF1. And the good news there is that they're not going to kill a tremendous amount of people. So most of your tornadoes are going to be at the lower end, and they won't kill as many people. But then look to the far right. While you don't have very many of the EF4 and EF5s in a given year, unfortunately, the few that you have are going to kill a tremendous number of people. So this is an interesting graphic here, going from the 50s to the 2000s. And this is not, you know, how many tornadoes do you have, or how big are they? Are they lasting longer, staying on the ground longer? This is just looking at tornado deaths. And what's happened from the 1950s on to now is that we've had the development of Doppler weather radar. And that allows us to see pretty clearly where we think a tornado is about to form. We've gotten much better at getting warnings out to people in time to try to get them to safety. Okay, so tornado forecasting. A tornado watch versus a tornado warning. You're going to need to know the difference here for your exam. Easy stuff. A tornado watch is issued whenever the conditions are favorable that tornadoes could form. Okay, so if there's a supercell thunderstorm in your area, if there's a squall line thunderstorm or dry line thunderstorm in your area, or if there is a tropical storm or hurricane hitting your area, they are going to go ahead and issue a tornado watch. It means be on the lookout. And these These watches cover a pretty big area, usually 26,000 square kilometers, and they can last for quite a while. It just depends on how long that threat is in your area. Here we go. The difference between watch and warning. So the tornado warning is not issued until a tornado has actually formed. Okay, so it's either been sighted on the ground by people or it is indicated on Doppler weather radar. So the difference between the watch and the warning is big. In the tornado watch, you want to be on alert. That's not a time to go take a 5-hour nap by yourself, with your earbuds in, ignoring the world. That's not a good time to do that. The tornado warning is issued when there's a tornado within your warning area, and that's when you want to actually take cover. Okay, so again, Doppler weather radar is just a wonderful invention, and it has allowed us to image where tornadoes are likely to form. And the tornadoes have something they refer to as a hook echo. Sometimes they might refer to it as a bow echo. We should have an image coming up. So this is a map of where you have Doppler radar weather sites in the United States. Okay, so we have several. I might argue we don't have enough. We've only got 3 in North Carolina. We've only got 1 in my home state of West Virginia. Well, these things are not cheap. And then there on the right, you have a mobile Doppler weather radar. And they're standing right in front of a tornado forming. Okay, so what do we mean by a bow echo or a hook echo? That's what you see here. And there's 2 different radar images. There's reflectivity on the left and then velocity on the right. And notice where that town is. That's called Moore. Is that necessarily Moore, Oklahoma? Actually, it might be. Moore, Oklahoma has been hit with large tornado outbreaks more than once in recent decades. Anyway, so you kind of see, especially the image on the left, I guess, if you follow the red and the orange, you kind of see it kind of dip down and it forms this hook image. That's what they mean by a hook echo or a hook, a hook echo or a bow echo. When they see this on the radio, they're going to go ahead and put out a tornado warning for that area because it's very likely that a tornado is forming at that time. So, again, our tornadoes have intense low pressure within the center, and this is causing air to basically move very quickly into the center. So your top wind speeds can get to as high as, I believe it's about 305 miles per hour. That's if it's an EF5 tornado. Okay, now we're looking at some older images. So these are prior to 2011. I believe these are in the late 90s. We'll just quickly flip through these images. Okay, so on this slide, just some review here. Remember, your tornado season is April through June. They tend to be associated with supercell thunderstorms along cold fronts, but also your dry lines and squall lines, and tropical storms and hurricanes. So in class, for any semester that we get to be in class, even if it's just once a week, I will use a pencil or pen and we will demonstrate how wind shear, in this particular case with the tropical storm Hermine as it moved into Texas earlier in the 2000s, your wind shear was not so much a difference in wind speed, but the winds were blowing perpendicular to each other. And that created that rolling horizontal tube of air that then was caught up in an updraft and turned vertical and formed a tornado. And again, this was in conjunction with a tropical storm. Okay, so exam question. I'm going to want you guys to know which year had probably the worst tornado outbreaks um, in probably at least 100 years of reporting. And that answer is 2011, spring of 2011. Okay, so between April 14th and 16th, you had more than 155 tornado outbreaks across 16 states. And not just your states in the Midwest in Tornado Alley, but also North Carolina. We had at least 30 confirmed tornadoes in North Carolina over that 3-day period, including an EF5. It was a mile wide, which is huge, and it stayed on the ground much longer than they normally do. It used to be the average path was about 6 miles. This EF3 that was a mile wide traveled 63 miles, hit Raleigh, Sanford, Esquivel, Fayetteville, and Dunn. So this image made national news. This was the Lowe's in Sanford, and everybody there lived. There were employees in the store, there were people shopping in the store, and employees took everybody into an interior stock room, I guess it was, and I guess that was towards the back of the store. So there they might have had a little luck on their side that it was appeared to be, well, looking at the parking lot, basically just like the right half of the store, they lost the entire roof. They lost the outer walls in the front and perhaps on the back. Anyway, long story short, the employees did the right thing and everybody lived through this. So here we are looking at cars that have been damaged in Esquivel. And look at these cars. They've clearly like rolled over many times. And then look at that tree over there on the left. You have pieces of sheet metal just wrapped around that tree. That's only going to happen when you have incredibly high winds. And again, this was an EF3. Here's another image of Esquivel. Here's an image of overturned cars piled up in Cumberland. Okay, so then later, and that's a typo, that should say April 22nd, 2011, St. Louis, Missouri got hit really bad. This is a before and after image of a neighborhood. Later still in April, the 25th through the 28th, 305 tornadoes. This time they stretched from Texas to New York. New York is not used to getting tornadoes. This was really bad. You had 21 F3s, those are horrible, 12 F4s, which are even worse, and 3 F5s, which are just catastrophic. So nearly 350 people killed, mostly in Alabama, and Tuscaloosa was very hard hit. Okay, so then into May, Joplin, Missouri. Just one tornado, but it was an EF5. So it was devastating. Killed over 100 people, wind speeds well over 200 miles an hour. Everywhere you looked in Joplin, just complete destruction. Everything reduced to rubble, just pieces of wood. Trees snapped off. Here we go. Finally, we have this information in English units. So the old school way of looking at tornadoes is that on average they'd be between 500 and 2,000 feet across. Well, they're getting bigger, okay? And that one that hit Raleigh in 2011 was a mile across, which is 5,280 feet. They tend to move across the landscape at about 30 miles per hour. They used to cut a path of about 6 miles. They're definitely bigger and longer lasting than they used to be. Again, that EF3 that hit Raleigh stayed on the ground for 63 miles, 10 times the average. Here's another look at the Fujita scale. We've seen this image before. Okay, so tornadoes can be difficult to forecast. I mean, you can't just call warnings every time you have a supercell thunderstorm, but you should at least call for a watch every time you have a supercell thunderstorm, just to let people know to be on the lookout. So your warning area, here we have English units, 25,000 square miles. And of course, the warning is not going to be issued unless a tornado is either sighted or is indicated on Doppler radar. Now we're looking at some older stuff here, older than 2011. Oh, look at this. A flimsy piece of wood now sticking into concrete on the side of a building. When we say that you have to be wary of projectiles in tornadoes, this is what we mean. This is what high winds can do. You can't walk up to the side of that building with a flimsy piece of wood and just manage to get it to stick into that concrete. It requires very high wind speeds for that to happen. Usually, when the tornado is occurring, they don't yet know what category it is. They don't assign it a Fujita scale number until after it's over, and then they go in and they look at the damage, and they can tell from assessing the damage what the wind speeds were.